There are places where matter is pressed so tightly together that the rules we live by begin to soften, where distance loses meaning, where time behaves differently, where nature holds itself at the very edge of what is allowed. If this quiet journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep these calm explorations alive, and I hold that support with sincere thanks. Now, let's begin with the first truth. Part 1. What do we mean by extreme? When we hear the word extreme, we often imagine destruction, explosions, collapse, violence. But in physics, extreme has a quieter meaning. It refers to limits. The furthest a force can go, the densest matter can become, the point where familiar rules begin to bend. To understand the most extreme object in the universe, we must first understand what it means for nature to reach its edge, not suddenly but patiently, under laws that never break, only transform. In everyday life, extreme is something loud, a storm tearing across land, a fire burning out of control, a mountain peak rising higher than any other. These are extremes of scale and energy that our senses can register. But the extremes that shape the cosmos often arrive without noise. They emerge slowly, over millions or billions of years, guided by equations that never rush and never hesitate. In physics, an extreme is not chaos, it is precision taken to its limit. Consider temperature. There is a highest temperature we can meaningfully describe, where particles move with such energy that distinctions between forces begin to blur. Consider speed. Nothing with mass can exceed the speed of light, not because it hasn't tried, but because the structure of reality itself forbids it. Consider density. There is a point where matter is packed so tightly that adding more does not simply make it heavier. It changes its very nature. These limits are not failures of physics. They are its boundaries. And boundaries are where the most interesting things happen. If you sit quietly for a moment and imagine turning a dial, slowly increasing gravity, you begin to see what extreme really means. At first, nothing dramatic happens. Objects simply feel heavier. Structures compress. Atmospheres grow thicker. But keep turning that dial, and subtle changes begin to accumulate. Atoms are squeezed closer together. Electrons are forced into smaller spaces. Press harder still, and the rules that once governed chemistry give way to rules that govern nuclei. At no point does nature panic. It adjusts. This is one of the most important ideas to hold as we continue. Extreme objects are not violations of natural law. They are expressions of it, carried to their furthest possible conclusions. They are what happens when gravity, quantum mechanics, and relativity are all asked the same question at once, and none of them are allowed to look away. In human terms, extremes feel dangerous because they are unfamiliar. But to the universe, they are simply rare configurations, solutions to equations that require very specific conditions and a great deal of time. A mountain forms where pressure and tectonics align. A diamond forms where carbon is held just tightly enough for long enough. And the most extreme cosmic objects form where mass, gravity, and time patiently conspire. There is also an important distinction between extreme and destructive. Destruction implies an end. But many extreme objects are remarkably stable. Some persist for billions of years, unchanged in any meaningful way. They are not transitional. They are not fleeting. They are long-term arrangements of matter that exist precisely because the laws of physics allow them to. This is why black holes often dominate conversations about extremity. They feel final. But extremity does not require disappearance. In fact, some of the most extreme states of matter remain visible, measurable, and astonishingly orderly. To understand this, we must shift how we think about strength. In everyday language, strength is about resistance, how much force something can endure before it breaks. In physics, strength is often about balance, about opposing forces meeting each other so perfectly that neither wins outright. A star exists because gravity pulls inward, while nuclear fusion pushes outward. Life on Earth exists because forces cancel just enough to create stability. An extreme object is often one where this balance is pushed to its narrowest possible margin. Imagine standing on a ridge so thin that a single step would send you falling, yet you remain standing. not by chance, but because every muscle, every sense, every adjustment is perfectly aligned. That is what many extreme cosmic objects are doing. They are not falling apart. They are not collapsing further. They are holding themselves together with astonishing precision. This idea becomes even clearer when we think about scale. Extremes are relative. A pressure that would crush a human is trivial to a planet. A temperature that vaporizes steel is routine inside a star. What makes an object truly extreme is not how it compares to us, but how close it sits to the absolute limits defined by nature itself. And those limits are surprisingly few. There is a maximum speed, a smallest meaningful length, a highest stable density before matter must rearrange itself into something new. Physics does not allow infinite anything. Every quantity has a boundary, and the universe seems deeply invested in exploring those boundaries without crossing them unnecessarily. When an object approaches one of these limits, something subtle happens. The equations we use every day stop being sufficient. Newton's laws give way to Einstein's. Classical intuition yields to quantum behavior, not because the old rules were wrong, but because they were incomplete. This is why extreme objects are so valuable to science. They are not curiosities. They are tests. Each one asks the same quiet question: do our laws still work here? And so far, remarkably, they do. Even in the most compressed environments, even under gravitational fields so intense that time itself slows measurably, the universe remains lawful, predictable, consistent. Strange, yes, but never arbitrary. There is something deeply calming about that. It means that no matter how far we push our understanding, we do not fall into chaos. We encounter structure. We encounter deeper order. The universe does not become less comprehensible at its edges. It becomes more demanding of precision, more respectful of patience. As you breathe right now, gravity is holding you gently to the surface of a planet. That same force, when allowed to act without interruption for millions of years on something vastly more massive, creates environments that feel unimaginable. Yet they arise from the same equation, the same constant, the same quiet pull. This continuity is what allows us to speak about extremes without fear. They are not alien intrusions into reality. They are reality, uninterrupted. So when we say the most extreme object, we are not looking for the loudest, the most violent, or the most dramatic. We are looking for the place where nature has been pushed as far as it can go without breaking itself, where matter is arranged in the most demanding configuration that still obeys the rules. That is the standard. And once we adopt it, the question becomes more interesting and more precise. If extreme means standing at the boundary without crossing it, if it means endurance rather than destruction, if it means stability under impossible conditions, then we must ask, very carefully, which object truly lives closest to that edge? Because as we continue this quiet journey, one thing will become clear. The most extreme object in existence is not defined by what disappears, but by what remains. Part 2. Why black holes seem like the ultimate answer. Black holes feel like the obvious choice. Regions where gravity overwhelms everything else, where light cannot escape, where time itself slows almost to a stop. They dominate our imagination because they sit at the boundary between the known and the unknowable. But while black holes are extraordinary, they are not the end of the story. They are not where matter reaches its final limit. When most people think of the most extreme object in existence, their minds arrive at black holes almost instantly. It makes sense. Few ideas in science feel as absolute. A place where escape is impossible, where familiar physics appears to vanish behind a silent horizon. Black holes feel final, like punctuation marks at the end of a sentence written by gravity itself. And yet, that feeling of finality is part of the illusion. To understand why, we need to look carefully at what a black hole actually is, and just as importantly, what it is not. A black hole is not an object in the traditional sense. It does not have a surface you can stand on or a structure you can probe and examine. It is a region of space-time defined by a boundary, a threshold beyond which information cannot return. That boundary, the event horizon, is what makes black holes feel so extreme. Cross it and nothing comes back. Not light, not matter, not signals. From the outside, whatever falls in simply fades away, frozen and reddened, slipping beyond reach. But notice something subtle here. From the perspective of the outside universe, the black hole is defined not by what happens inside, but by what we can no longer observe. Its extremity is one of invisibility, not endurance. It is an edge beyond which our questions stop being answerable, not because the laws of physics fail, but because the information becomes inaccessible. This distinction matters. When matter falls into a black hole, it does not become more complex, it becomes less visible. The black hole itself is astonishingly simple. It can be described by just a few properties: mass, spin, and charge. Everything else, the details of atoms, the structure of matter, the history of what fell in, is erased from the outside view. Physicists sometimes describe this as nature smoothing things out. In that sense, black holes are not places where matter reaches its most intricate or strained state. They are places where complexity disappears. They are cosmic erasers, not cosmic tests of endurance. This is why black holes, for all their drama, may not represent the most extreme condition matter can sustain. To see this more clearly, imagine increasing gravity again, slowly, patiently. As mass accumulates, objects compress, stars burn hotter, cores grow denser. Eventually, nuclear reactions fail, and gravity begins to dominate. But before a black hole ever forms, matter passes through stages that are far more demanding than the final collapse itself. A black hole represents what happens when matter can no longer resist gravity at all. But extremity is often more interesting when resistance still exists. Think of it this way. A bridge that collapses under weight is not demonstrating strength. The bridge that holds just barely, every beam strained, every joint stressed, is showing you its true limits. The moment before failure is where structure, balance, and resistance are pushed to their maximum. Black holes are what come after that moment. Once a black hole forms, the struggle is over. Gravity has won completely. Matter no longer pushes back in any meaningful way. The internal details, whatever they may be, are hidden forever behind the horizon. The universe, from the outside, no longer needs to negotiate with the object. It only needs to measure its mass and move on. This makes black holes paradoxically simple. They are extreme in consequence, but not in complexity. There is also something else to consider. From the outside, the event horizon of a black hole is not a place of violence. An object falling through does not feel sudden jolt at that boundary. Locally, nothing special happens at the horizon itself. The drama exists in our descriptions, not in the physics experienced at that moment. The real extremity of black holes lies deeper, near what we call the singularity. But this is where our understanding becomes incomplete. Our current theories cannot fully describe what happens there. General relativity predicts infinite density, but infinities are usually signs that a theory has been pushed beyond its valid range. So when we point to singularities as evidence of ultimate extremity, we must be careful. We are pointing to a gap in our knowledge, not a confirmed physical state. This is another reason black holes feel like the ultimate answer. They occupy a region where our equations stop giving us clean results. But ignorance should not be confused with extremity. The fact that we cannot see inside does not mean that what lies there is the most refined, balanced, or demanding arrangement nature can produce. It simply means we are no longer allowed to look. There is something deeply human about mistaking disappearance for depth. When something vanishes beyond reach, it feels profound. But physics often finds its richest insights not where things vanish, but where they remain, under pressure, under strain, refusing to collapse. And this is where black holes quietly step aside. Before matter becomes a black hole, it must first survive conditions that are, in many ways, more extreme. Pressures so intense that atoms are destroyed. Densities so high that electrons and protons are forced into new arrangements. Gravity so strong that space and time already behave strangely, yet matter still holds together. These are the conditions where physics is not erased but tested. Black holes do not allow us to study matter under ultimate stress because they hide it. They remove the experiment from view. What remains observable is the aftermath, not the struggle itself. This is why, despite their reputation, black holes may not deserve the title we instinctively give them. They are endpoints, not balancing acts. They are conclusions, not negotiations. They are what happens when the universe decides that no further structure can be sustained in the open. And yet, the universe is remarkably reluctant to reach that decision. For every black hole that forms, there are countless objects that approach the brink and stop. Objects that resist gravity not through fusion, not through radiation, but through the deepest rules of quantum mechanics. Objects that remain visible, measurable, and astonishingly stable while operating at the edge of possibility. Black holes capture our imagination because they feel like cosmic mysteries. But extremity, as physics defines it, is not about mystery alone. It is about how far known laws can be pushed before something gives way. And in that sense, black holes may be less extreme than they appear. They represent a surrender, not a stand. As we continue, the question becomes sharper and more interesting. If black holes are not the final measure of extremity, if they are what comes after resistance fails, then what objects represent resistance at its absolute maximum? Where does matter hold itself together under the greatest known pressure without vanishing behind a horizon? Where do the laws of physics work the hardest, not to erase structure, but to preserve it? Those questions lead us away from disappearance and toward endurance, away from invisibility and toward measurable strain, away from black holes and toward something quieter, smaller, and far more demanding. And that is where our journey goes next. Part 3. The quiet life and death of massive stars. Long before any extreme object exists, there's a star living a patient life, fusing atoms in its core, holding itself up against gravity through steady nuclear fire. When that balance finally fails, gravity wins, not violently at first, but inevitably. The path a star takes after death determines whether it becomes something familiar or something far stranger. For most of its existence, a star is an exercise in calm balance. Gravity pulls inward, trying to compress the star into something smaller and denser. At the same time, nuclear fusion in the core releases energy that pushes outward. These two forces meet in a quiet standoff that can last for millions or even billions of years. From the outside, the star appears steady, constant, reliable. But inside, an immense struggle is always underway. In stars like our Sun, this balance is relatively gentle. Hydrogen fuses into helium, releasing just enough energy to counter gravity. The pressures are immense by human standards, but modest by cosmic ones. The Sun will live this way for billions of years, slowly and predictably, before it eventually exhausts its fuel and drifts toward a peaceful end. But not all stars live such quiet lives. Some stars are born massive, many times heavier than the Sun. Their gravity is stronger from the very beginning, and to survive it, their cores must burn hotter and faster. These stars race through their fuel, fusing hydrogen at an enormous rate. What feels like abundance is actually urgency. The brighter and more massive a star is, the shorter its life tends to be. Even as you sit still right now, there are stars in the cosmos that have already lived their entire lives in the time it takes others to barely begin. As fusion progresses, the star's core slowly changes. Hydrogen becomes helium. Helium becomes carbon. Carbon can fuse into heavier elements like neon, oxygen, and silicon. Each new stage of fusion releases less energy than the one before. The outward pressure weakens, while gravity never relaxes its grip. Eventually, the star reaches a quiet but decisive moment. Iron. Iron is the end of the road for stellar fusion. Fusing iron does not release energy, it consumes it. When a massive star builds an iron core, it unknowingly signs its own fate. The delicate balance that sustained it for millions of years can no longer be maintained. And yet, even here, there is no explosion at first. There is a pause. The core grows heavier. Gravity tightens. Electrons are forced closer together. The star begins to lose the ability to hold itself up using ordinary pressure. But collapse does not happen all at once. Nature always gives matter a chance to respond. As the core compresses, electrons begin to resist. This resistance comes not from heat but from quantum mechanics. A principle known as electron degeneracy pressure arises, preventing electrons from being squeezed into identical states. For a time, this pressure can halt collapse, even in the face of crushing gravity. This is how white dwarfs are born. In smaller stars, electron degeneracy pressure is enough. The collapse stops. The star sheds its outer layers gently, leaving behind a dense, Earth-sized core that cools quietly for trillions of years. This is a stable ending, a peaceful retirement for a star that never grew too large. But for truly massive stars, even this resistance is not enough. Gravity continues to press inward. Electrons are pushed into protons, merging to form neutrons. In a matter of seconds, the core transforms into something entirely new. At this point, the collapse accelerates dramatically. The star's outer layers may rebound violently, creating a supernova, one of the brightest events the cosmos ever produces. Yet the explosion itself is almost secondary. The real story is what happens at the center. As the core collapses, it becomes so dense that atomic structure is erased, nuclei dissolve, matter becomes a tightly packed sea of neutrons. For a brief moment, gravity is resisted once again, this time by neutron degeneracy pressure and the strong nuclear force. This is the birth of something extreme, but not inevitable. Whether the collapse stops here or continues depends on one thing: mass. If the remaining core is light enough, the pressure of neutrons can halt the collapse. The star does not disappear. It does not become a black hole. Instead, it becomes a neutron star, a compact, stable object where matter is packed to its absolute limit while still resisting gravity. If the core is too massive, even neutron pressure fails. Gravity finally wins completely, and a black hole is born. This branching point is one of the most important thresholds in astrophysics. It tells us that extreme objects are not accidents. They are outcomes selected by mass, time, and the quiet patience of physical law. A star does not choose its fate. It follows it, step by step, as gravity slowly removes every option except one. What is remarkable is how narrow these paths are. A difference of just a few solar masses can determine whether a star ends as a white dwarf, a neutron star, or a black hole. There is nothing arbitrary about this. The universe is precise, unforgivingly precise, and yet it allows for multiple endings, each governed by different balances of force. Throughout this entire process, there is no intention, no drama, no violence in the emotional sense. Even supernovae, for all their brightness, are simply pressure release valves. The star is not exploding out of anger or instability. It is responding to the removal of support. Gravity does not attack, it waits. And when support vanishes, it moves inward, exactly as it always has. This slow inevitability is what makes stellar death so important to our understanding of extremes. It shows us that the most exotic objects in existence are not born in chaos, but in patience. Millions of years of equilibrium give way to seconds of collapse, all dictated by rules that never change. As you breathe right now, fusion reactions are happening inside the sun, holding gravity at bay. The same laws that govern those gentle reactions also govern the collapse of massive stars into neutron stars or black holes. There is no separate set of rules for the extreme, only the same rules applied under more demanding conditions. This continuity is essential. It means that when we study the death of massive stars, we are not studying something alien. We are studying the future of gravity itself, playing out under different constraints. We are watching matter answer the question, how much pressure can you endure before you must become something else? And crucially, we see that collapse is not the end of structure. Even after a star dies, its core may become one of the most ordered, stable objects in the cosmos. A neutron star is not debris, it is not rubble. It is a precisely balanced remnant, shaped by forces that have reached their limits but have not yet broken them. This is why massive stars matter so much in our search for the most extreme object. They are the gateways, the slow, luminous beginnings that eventually lead to the densest, most demanding states matter can occupy while remaining visible. Before there is extremity, there is endurance. Before there is collapse, there is balance. And before any star becomes strange, it lives a long, quiet life doing exactly what physics allows, no more and no less. As we move forward, we leave the glow of living stars behind and focus on what remains when fusion finally goes silent. Because the true extremes of the cosmos are not born in fire. They are born in stillness. Part 4. When gravity almost wins but not quite. There exists a moment in stellar collapse where gravity pushes inward with unimaginable strength, yet something pushes back. Not fusion, not radiation, but the quantum rules written deep inside matter itself. This moment gives rise to objects so dense that a teaspoon would outweigh mountains, yet they do not become black holes. This narrow escape creates one of the universe's most delicate balances. To understand how close gravity comes to absolute victory, imagine collapse not as a sudden fall, but as a tightening spiral. The core of a massive star contracts, layer by layer, pressure building steadily as space grows more crowded. Atoms are squeezed until their boundaries blur. Electrons are pressed into regions they would rather not occupy. Gravity does not rush. It simply continues inward, patient and exact. At first, familiar forces resist. Heat from fusion once pushed back against collapse, but that era has ended. Radiation pressure fades. The star's core grows heavier, quieter, more compact. Then, at a scale far smaller than atoms, something unexpected intervenes. Not a force you can feel, but a rule you cannot break. This rule is quantum mechanical, and it is absolute. Electrons, it turns out, are not allowed to be identical in the same way. A principle known as the Pauli exclusion principle states that no two identical fermions can occupy the same quantum state at the same time. This is not a preference, it is not a tendency. It is a prohibition woven into the mathematics of reality. As gravity compresses the core, electrons are forced into higher and higher energy states simply because they cannot all fit into the lowest ones. This creates a pressure that does not depend on temperature. It does not weaken as the star cools. It exists purely because of quantum rules. This pressure, electron degeneracy pressure, is astonishingly strong. Strong enough, in some stars, to stop collapse entirely. Strong enough to hold up a stellar core against gravity for billions of years. This is the quiet strength behind white dwarfs. But in the most massive stars, even this is not enough. Gravity continues to push. Electrons are driven into protons. Neutrinos escape in vast numbers, carrying energy away. What remains is a core made almost entirely of neutrons, particles far denser than anything electrons ever formed. At this point, collapse becomes almost unimaginably fast. In a fraction of a second, a core larger than Earth is crushed into a sphere barely tens of kilometers across. Matter reaches densities found nowhere else in the observable cosmos, and still, gravity does not fully win. Once again, quantum rules intervene. Neutrons, like electrons, obey the Pauli exclusion principle. They too refuse to share quantum states. As they are packed together, neutron degeneracy pressure rises sharply. At the same time, the strong nuclear force, normally confined to the tiny distances inside atomic nuclei, begins to play a role on macroscopic scales. Neutrons attract each other at very short distances, adding another layer of resistance to collapse. This is the last stand. Here, gravity presses inward with enough force to bend space-time itself. Time slows. Light struggles to climb away. The curvature of space becomes extreme. And yet, at this precise threshold, matter finds a way to hold together, not through heat, not through motion, but through rules written into the deepest structure of reality. The result is a neutron star. This moment is what makes neutron stars so special. They are not simply dense objects. They are objects that exist at the very edge of possibility. A little more mass, and gravity overwhelms every form of resistance. A little less, and the object would never have formed at all. Balance here is not gentle, it is exact. If you could somehow approach this moment, if you could pause the universe at the instant collapse nearly completes, you would see a configuration so finely tuned that it feels almost improbable. But it is not chance. It is consequence. The outcome of competing laws meeting at their limits. This is what it means when we say gravity almost wins. Unlike black holes, neutron stars do not hide this struggle. They display it openly. Their mass remains accessible. Their surfaces exist. Their gravity can be measured directly. Their spin, their magnetic fields, their emissions all carry signatures of matter under maximum stress. In a black hole, collapse ends the conversation. In a neutron star, the conversation never stops. Every second, the star's interior remains under pressure so intense that ordinary descriptions fail. Matter behaves in ways we cannot reproduce on Earth. Nuclei are crushed into exotic arrangements. The line between particle and field blurs. Some theories suggest that deep inside, matter may exist in unfamiliar phases, superfluids, superconducting states, or even free quark matter. But what matters most is this: whatever is happening inside, it is stable. The star does not continue collapsing. It does not expand. It does not disintegrate. It holds its shape with astonishing resilience, sometimes for billions of years, orbiting silently through space as a reminder that gravity does not always get the final word. There is something profoundly calming in this idea. The strongest force in the universe can be resisted, not indefinitely, not everywhere, but under the right conditions. Nature has built-in safeguards that prevent immediate collapse into nothingness. These safeguards are not ad hoc, they are fundamental, and they only reveal themselves when the universe is pushed hard enough. As you breathe right now, quantum rules are shaping the solidity of the floor beneath you. They prevent atoms from collapsing into one another. They give matter its structure. In neutron stars, those same rules are asked to do far more, to support masses greater than the sun within volumes smaller than a city. They succeed. This is why neutron stars feel more extreme than black holes in a very specific sense. They represent resistance at its maximum. They are the last stable configuration matter can achieve before disappearance becomes inevitable. They are not failures of gravity. They are compromises. It is also worth noting how narrow this compromise is. Add too much mass, perhaps from a companion star or through a collision, and the balance tips. Neutron degeneracy pressure has limits. The strong nuclear force has limits. Beyond a certain threshold, even these cannot stop collapse. When that happens, the star does not slowly adjust. It gives way. But until that precise moment, the neutron star remains intact, spinning, pulsing, radiating. It exists in a state that feels almost defiant, not because it resists change actively, but because it obeys rules that gravity must also respect. This narrow window, where gravity is almost victorious but not quite, is where some of the most fascinating physics in the cosmos resides. It is where relativity, quantum mechanics, and nuclear physics all meet, none fully dominant, none fully silent. And importantly, it is where we can still observe. We can measure neutron star masses. We can watch their spins slow over time. We can detect the gravitational waves they emit when they merge. We can listen to the faint ticking of pulsars, precise beyond anything humans have built. All of this is possible because neutron stars have not vanished. They remain. So when we talk about extreme objects, we must be careful not to confuse finality with intensity. The most demanding states of matter are not always the ones that disappear into darkness. Sometimes they are the ones that stay behind, quietly bearing the weight of forces that nearly tore them apart. As we continue, we will look more closely at what these objects are made of, how dense they truly are, and why their very existence forces us to rethink what matter can be. Because the story of extremity does not end when gravity almost wins. It becomes more interesting precisely because it doesn't. Part 5. Neutron stars. Matter stripped to its bones. A neutron star is what remains when electrons and protons are crushed together, forced to merge. What's left is matter reduced almost entirely to neutrons, packed tighter than anything else we can directly observe. These stars are small, silent, and heavier than entire solar systems. They are not chaotic, they are precise, and they are only the beginning. To picture a neutron star, it helps to first let go of familiar scales. These objects are typically no wider than a large city, 20 kilometers across, sometimes less. And yet within that narrow sphere is packed more mass than the sun, not spread out, not glowing across millions of kilometers, but concentrated, held together by gravity so strong that it reshapes everything nearby. If you could stand on the surface of a neutron star, the view would be strange beyond words. The horizon would curve sharply upward, not because the world is small, but because gravity bends space itself. A step would feel impossible. A fall would be instant. Light would arc gently, no longer traveling in straight lines. Even time would move more slowly here, stretched thin by the star's immense mass. But this surface, this boundary between star and space, is already a kind of miracle. Because beneath it lies matter in a state that should not exist for long. Matter so compressed that ordinary atomic structure has been erased. No electron clouds, no atoms as we know them. Just a dense lattice of neutrons pressed together until the distinction between one and the next becomes subtle. In everyday matter, empty space dominates. Atoms are mostly void, with tiny nuclei surrounded by vast regions where electrons roam. In a neutron star, that emptiness is gone. Gravity has removed it. Nuclei touch, then dissolve. What remains is something closer to a single gigantic atomic nucleus, one the size of a city. And yet, this nucleus does not collapse further. That fact alone should give us pause. The forces holding a neutron star together are not the ones we encounter in daily life. Pressure here is not about heat or motion. It is about quantum rules and nuclear interactions operating at their absolute limits. Neutrons resist being forced into identical states. The strong nuclear force provides a short-range attraction that adds cohesion without allowing collapse. The result is a structure that is both fragile and incredibly strong. Fragile because it exists only within a narrow range of mass. Strong because within that range, it can endure conditions that would annihilate anything else. Consider density. A teaspoon of neutron star material would weigh billions of tons on Earth, not because it is magically heavy, but because the same amount of matter that once filled mountains has been squeezed into a space smaller than a grain of sand. Density here is not metaphorical, it is literal. Matter is as close together as the laws of physics allow without erasing its identity entirely. And still, the star remains stable. This stability gives neutron stars a kind of quiet authority. They do not shine like ordinary stars. They do not burn fuel. Their light, when it appears, often comes from rotation and magnetism rather than heat. Many neutron stars are barely visible at all unless they are spinning in just the right way or interacting with nearby matter. Yet despite their silence, they are among the most precisely measurable objects we know. Some neutron stars rotate hundreds of times per second. Their spin rates are so consistent that they rival atomic clocks. Others emit narrow beams of radiation that sweep across space as the star turns. When one of these beams crosses Earth, we detect it as a pulse, steady, predictable, unchanging over years. These pulsars are not accidents. Their regularity comes from their extreme compactness. When a massive star collapses into a neutron star, conservation of angular momentum forces it to spin faster, much like a figure skater pulling in their arms. A star that once rotated leisurely may suddenly spin dozens or hundreds of times per second. And because neutron stars are so rigid, that spin remains stable. This rigidity is another sign of matter stripped to its bones. On Earth, materials flex, deform, and flow under stress. In neutron stars, deformation is minimal. The crust, just a kilometer or two thick, is thought to be the strongest material in the known universe. Not because it is unbreakable, but because breaking it requires stellar-scale forces. When that crust does crack, the result can be sudden and dramatic. Starquakes release enormous amounts of energy, briefly altering the star's rotation or magnetic field. But even these events do not destroy the star. They are adjustments, not failures. Beneath the crust, conditions grow even stranger. The interior of a neutron star is not fully understood, and that uncertainty is part of what makes these objects so important. At increasing depths, neutrons may flow as a superfluid, moving without friction. Protons may form superconducting states. Magnetic fields may thread through the star in quantized tubes. The familiar division between solid, liquid, and gas loses meaning. Some theories suggest that at the very center, matter may transition into even more exotic forms, perhaps a soup of free quarks, no longer bound into neutrons at all. If such a core exists, it would represent a new phase of matter, one that cannot be created or sustained anywhere else we know. But whether or not this happens, the broader picture remains the same. A neutron star is not a chaotic mess. It is layered, structured, governed by precise rules that change with depth, pressure, and density. This layered complexity is what separates neutron stars from black holes in a profound way. Black holes hide their interiors. Neutron stars expose theirs, indirectly, through mass measurements, spin rates, thermal emissions, and gravitational effects. They allow us to test theories of matter under conditions that cannot be replicated on Earth. Every neutron star is a natural experiment running continuously, silently, for millions or billions of years. And each one asks the same question in its own way. How far can matter be pushed before it must give up its identity? So far, neutron stars represent the furthest known answer. They are not infinite. They are not singularities. They are matter, still matter, arranged in the most demanding configuration nature permits while remaining visible and stable. That alone makes them extraordinary. There's also something humbling in their scale. Despite their mass, neutron stars are easy to miss. They do not dominate the night sky. Many drift alone, cold and dark, remnants of explosions long faded. Others orbit companions quietly, drawing matter in slow spirals. Their presence is subtle unless you know where and how to look. And yet, their influence is immense. Neutron stars shape the evolution of galaxies by seeding space with heavy elements during their formation. Their collisions generate gravitational waves that ripple across the cosmos. Their magnetic fields and radiation can sculpt surrounding matter, affecting star formation and cosmic chemistry. All of this arises from matter stripped to its bones, from atoms denied their space, from particles forced into new arrangements, from gravity allowed to push almost, but not quite, to the end. As we move forward, this precision becomes even more striking. Because neutron stars are not all the same. Some push rotation to extremes, others push magnetism beyond comprehension. Each variation explores a different edge of what is allowed, and through them, we begin to see a pattern. The most extreme objects are not those that vanish, they are those that remain, holding together under conditions that should not allow it. Neutron stars are not the conclusion of this story. They are its clearest evidence. Part 6. How quantum physics holds back a star. Inside a neutron star, gravity is relentless, but quantum mechanics whispers a firm refusal. A rule known as degeneracy pressure prevents identical particles from occupying the same state. This rule, quiet and mathematical, is strong enough to hold up a collapsed star. Here, the smallest laws of nature oppose the largest force in the universe, and neither yields easily. To appreciate how extraordinary this is, it helps to remember what gravity is trying to do. Gravity does not tire, it does not weaken with time. Given enough mass and enough patience, it always pulls inward, compressing matter toward smaller and smaller volumes. In a neutron star, gravity is so strong that mountains are flattened into centimeters, and space itself curves sharply toward the surface. Any ordinary structure would fail instantly. And yet, the star remains. The reason lies not in heat, not in motion, but in the deep architecture of matter itself. Quantum mechanics, often associated with uncertainty and probability, contains some of the strictest rules in all of physics. Among them is a principle that sounds simple, but carries enormous consequence. Identical particles cannot be identical in every way. Electrons, neutrons, and protons belong to a class of particles called fermions. Fermions obey the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state at the same time. This is not a force you can push against. It is not mediated by particles or fields. It is a rule of allowed arrangements. When matter is sparse, this rule goes unnoticed. There is plenty of room. Particles can spread out into different states without conflict. But when gravity compresses matter relentlessly, available states begin to fill. Particles are forced into higher and higher energy configurations simply because lower ones are already occupied. This creates pressure, not pressure from heat, which depends on temperature and motion, but pressure from arrangement. From the simple fact that the rules forbid further compression without increasing energy. This is degeneracy pressure. In a neutron star, this pressure becomes immense. At first, during collapse, it is electrons that provide this resistance. As they are squeezed together, their degeneracy pressure rises sharply. In smaller stellar remnants, this is enough to stop collapse entirely, creating white dwarfs. But in neutron stars, gravity overwhelms even this. Electrons are pushed into protons, forming neutrons and releasing neutrinos that escape into space. Now the burden of resistance shifts. Neutrons take over. Neutrons are far more massive than electrons, and packing them together raises degeneracy pressure even more steeply. But this happens only when densities become truly extreme. The star must compress itself to near nuclear densities before neutron degeneracy pressure can assert itself fully. This is why neutron stars are so small. They are not gently supported. They are compressed to the brink before resistance finally becomes strong enough to matter. At that point, something remarkable happens. Gravity continues to pull inward, but the cost of forcing neutrons into ever higher energy states becomes too great. The inward pull is matched moment by moment by an outward quantum refusal. The star finds equilibrium. This balance is unlike anything else in the cosmos. It does not depend on burning fuel. It does not radiate energy to maintain itself. It does not gradually weaken as time passes. Degeneracy pressure is not consumed. It does not run out. As long as the rules of quantum mechanics remain unchanged, the resistance remains. This is why neutron stars can persist for billions of years without significant structural change. But degeneracy pressure is not acting alone. At the densities found inside neutron stars, the strong nuclear force also becomes important. This force, which binds protons and neutrons together inside atomic nuclei, operates only over very short distances. In ordinary matter, it is invisible beyond the scale of a nucleus. In neutron stars, those distances become the norm. Neutrons pressed closely together experience a delicate balance of attraction and repulsion governed by the strong force. At certain separations, this force adds stability, resisting collapse further. At others, it can contribute to stiffness in the star's internal structure. The exact behavior of this interaction at extreme densities is still an active area of research. What matters for our story is this. The resistance inside a neutron star is not simple. It is layered. Quantum rules and nuclear forces intertwine, creating a complex equation of state that determines how matter responds to pressure at each depth. This equation of state is one of the great unknowns of modern physics. We cannot recreate these conditions on Earth. Particle accelerators can smash nuclei together briefly, but they cannot hold matter at neutron star densities. Laboratories cannot sustain pressures where atomic identities dissolve. So instead, we look to the stars themselves. By measuring neutron star masses in radii, by observing how they spin and how they deform during collisions, scientists can infer how stiff or soft their internal matter must be. Each observation constrains the possible ways quantum mechanics and nuclear physics behave under extreme compression. In this sense, neutron stars are not just objects. They are messages. They tell us that quantum mechanics, a theory born to explain the behavior of electrons in atoms, scales upward to hold back stars. That rules discovered to describe the microscopic world are not optional details, but load-bearing principles of the universe. There is something quietly astonishing about that. The smallest laws of nature do not disappear when things get big. They become decisive. Gravity may be the architect of cosmic structure, shaping galaxies and guiding stars. But it is quantum mechanics that sets the final boundaries. Gravity says how hard matter is pushed. Quantum rules say how far it can go, and neither can ignore the other. This tension is what makes neutron stars feel alive, even though they no longer burn. Inside them, forces are locked in continuous negotiation. Gravity presses inward with every kilogram of mass. Quantum mechanics pushes back with every forbidden state. The balance holds, not because either side is weak, but because both are exact. It is also important to understand how close this balance is to failure. There is a maximum mass a neutron star can have before degeneracy pressure and nuclear forces are no longer enough. Beyond this limit, known as the Tolman-Oppenheimer-Volkoff limit, collapse resumes. The star cannot find a new equilibrium. Gravity overwhelms all resistance and a black hole forms. This limit is not sharply defined because it depends on the unknown details of the star's interior. But observations suggest it lies somewhere around 2 to 3 times the mass of the Sun. That narrow window defines the entire class of neutron stars. Within it, matter holds. Beyond it, matter disappears. That thin margin makes neutron stars one of the most precarious stable objects in existence. They are not robust in the way planets are. They are stable only because the universe's rules are precise enough to allow it. And yet, within that precision, there is grace. Quantum mechanics does not struggle or strain. It simply enforces its rules. It does not know about stars or gravity or collapse. It only knows which states are allowed and which are not. That knowledge alone is enough to resist the weight of a sun. As you lie still now, the solidity of your body is maintained by the same principle. Electrons refuse to overlap. Atoms keep their distance. Matter holds its shape. The difference is not one of kind, but of degree. In neutron stars, the same refusal is amplified to cosmic proportions. This realization carries a quiet comfort. It means that even in the most extreme environments, the universe does not abandon its smallest truths. The rules that govern the tiniest particles are not overwhelmed by scale. They scale up. So when we ask how a star can be held up by quantum mechanics, the answer is not dramatic. It is consistent. Quantum rules do not bend for gravity. They do not negotiate exceptions. They apply everywhere, always, and when gravity pushes hard enough, those rules become the final barrier against collapse. That barrier is thin, it is precise, and it is enough. As we move forward, we will see how this balance expresses itself in motion, magnetism, and time itself. Because once matter is held at this extreme edge, even small variations, spin, field strength, alignment, can produce some of the most extraordinary phenomena we can observe. But beneath all of it, holding everything together, is a quiet refusal. The universe saying, in its smallest language, no further. Part 7. The speed that should tear a world. Apart, some neutron stars spin hundreds of times per second. Their surfaces move at a significant fraction of the speed of light. Any familiar object would tear itself apart under such strain. But neutron stars do not. Their gravity is so intense that even extreme rotation cannot free their matter. They remain whole, smooth, and terrifyingly stable. To understand why this is so astonishing, it helps to begin with something familiar. Imagine a planet spinning faster and faster. As its rotation increases, centrifugal forces grow stronger, pulling outward against gravity. At some point, those forces would overcome the planet's ability to hold itself together. Mountains would slump, oceans would surge toward the equator. Eventually, material would lift free, flung outward into space. This limit exists for every rotating object. Even stars have one. But neutron stars live far beyond the limits that apply to anything else we know. When a massive star collapses into a neutron star, it shrinks dramatically. A core that once spanned thousands of kilometers is compressed into a sphere only a few tens of kilometers wide. Angular momentum must be conserved. There is no exception to this rule. So as the radius decreases, rotation accelerates. What was once a slow spin becomes a blur. A neutron star that rotates 10 times per second is considered modest. Many rotate hundreds of times per second. Some approach 1,000 rotations every second. At those speeds, the surface is moving at tens of thousands of kilometers per second, an appreciable fraction of the speed of light. And yet, nothing flies off. The reason lies in the star's gravity. At the surface of a neutron star, gravity is not merely strong, it is overwhelming. The escape velocity, the speed needed to break free, can exceed half the speed of light. That means even matter racing sideways at incredible speed remains bound. Centrifugal force tries to pull matter outward, gravity pulls inward far more fiercely. The contest is not close. This balance gives neutron stars a kind of rotational freedom that feels almost unreal. They can spin faster than any solid object we could ever build, faster than planets, faster than ordinary stars, and still maintain a smooth, intact surface. In fact, the faster they spin, the more remarkable their stability becomes. This stability is also tied to their rigidity. Neutron stars are not fluid spheres like gas giants. Their crusts are thought to be incredibly stiff, composed of nuclei packed into dense lattices embedded in seas of degenerate particles. Deformation is minimal. When the star spins, it does not easily bulge or warp. Instead, it holds its shape with quiet authority. There's a theoretical upper limit to how fast a neutron star can spin, known as the breakup frequency. Beyond this rate, even gravity would no longer be able to hold matter at the equator. Calculations suggest this limit lies somewhere around 1 to 2,000 rotations per second, depending on the star's mass and internal structure. What is remarkable is how close some neutron stars come to this limit. These rapidly spinning stars, often called millisecond pulsars, rotate so steadily that their pulses arrive with extraordinary regularity. Their timing precision rivals the best atomic clocks on Earth. Some lose only a fraction of a rotation over millions of years. This regularity is not incidental. It is the natural outcome of extreme compactness and rotation combined. When an object is small, massive, and rigid, there is very little to disturb its motion. External torques have little effect. Internal friction is minimal. Once spinning, the star simply keeps going. There is something deeply soothing about that image, a remnant of a violent stellar death, now spinning calmly, steadily, marking time with unwavering precision. But the speed does more than create regular pulses. It reshapes the star itself. Rapid rotation flattens the star slightly, making it oblate. The equator bulges outward by a small but measurable amount. This deformation affects how gravity is distributed across the surface and how the star emits radiation. It also allows the star to sustain tiny asymmetries, imperfections in its mass distribution, that can generate gravitational waves. These waves are faint but persistent. As the star spins, any slight irregularity sends ripples through space-time, carrying energy away. Over immense timescales, this emission can slowly drain rotational energy, causing the star to spin down. The process is gentle, predictable. Another example of extreme physics unfolding without drama. It is important to notice how different this is from black holes. A black hole can spin extremely fast, but its rotation is hidden behind the event horizon. We infer it indirectly through effects on surrounding matter. A neutron star displays its rotation openly. It announces its speed through pulses, radiation, and timing. It invites measurement. This openness is part of what makes neutron stars feel more extreme in a tangible way. We are not merely speculating about hidden interiors. We are watching matter move at nearly light speed while remaining intact, stable, and predictable. Rotation also interacts with the star's magnetic field in powerful ways. Neutron stars often possess magnetic fields trillions of times stronger than Earth's. As the star spins, these fields sweep through space, accelerating charged particles and producing beams of radiation. The faster the spin, the more intense this process can become. In some cases, the combination of rapid rotation and strong magnetism produces environments so extreme that they distort atomic structure in surrounding space. Yet the star itself remains unchanged, continuing its relentless spin. This raises an important point about extremity. Extreme does not always mean unstable. We tend to associate high speed with fragility. Faster means more likely to break. More energy means more danger. But neutron stars invert this intuition. Their extremity lies in how well they tolerate conditions that would destroy anything else. Speed that should tear a world apart becomes simply another parameter in a stable equation. As you rest now, the Earth beneath you rotates once every 24 hours. That rotation defines your days and nights. It feels slow, gentle, reliable. A neutron star can rotate tens of thousands of times faster and yet feel just as reliable, at least from the perspective of physics. This contrast helps us recalibrate our sense of scale. Speed, like gravity, only feels extreme relative to the structures experiencing it. A neutron star is built for speed. Its compactness, its gravity, its quantum-supported matter all conspire to make such rotation not just possible, but natural. In fact, rotation is so integral to neutron stars that many would be invisible without it. Their emissions rely on spinning beams sweeping past observers. Without rotation, they would fade quietly into the background of space. So the speed that should tear them apart instead gives them voice. It allows them to signal their presence across vast distances. It lets us detect them, study them, and learn from them. Their rotation is not a flaw, it is a feature. There is something profoundly humbling in this. The universe can build objects that spin near the ultimate speed limit for matter, held together not by engineering, but by the interplay of gravity and quantum law. And it does so repeatedly, reliably, without spectacle. No alarms, no warning signs, just balance, held at the edge. As we continue this journey, we will see that rotation is only one way neutron stars explore extremity. Magnetism, density, and time itself are all pushed to their limits within these objects. But for now, let the image settle. A star's core, collapsed to the size of a city, spinning hundreds of times each second, matter racing near light speed, and nothing flying apart. Not because the forces are gentle, but because the balance is exact. And as we move onward, one question begins to form quietly in the background. If gravity can hold matter together even at these speeds, what happens when magnetism joins the conversation? Part 8. Magnetars, where physics begins to strain. Among neutron stars, some are born with magnetic fields so powerful they defy intuition. Magnetars can twist atomic structures from thousands of kilometers away. Their magnetic energy can crack their own crusts, releasing silent flashes that ripple across space. These objects are calm most of the time, but when they speak, the universe listens. To understand magnetars, it helps to begin with magnetism as we know it. On Earth, magnetic fields guide compasses, protect us from solar wind, and quietly shape much of our technology. Even the strongest magnets we can build in laboratories feel impressive only because our daily experience sets such a low bar. Compared to cosmic fields, they are whispers. A typical neutron star already possesses a magnetic field trillions of times stronger than Earth's. That alone is difficult to comprehend. But magnetars go further, far further. Their magnetic fields can be 1,000 times stronger than those of ordinary neutron stars. Strong enough that the field itself becomes a dominant source of energy, rivaling gravity and rotation in influence. At these strengths, magnetism stops being a background feature and becomes a structural force. The origin of such intense fields lies in the star's birth. When a massive star collapses, any magnetic field it possessed is compressed along with the core. Just as rotation speeds up through conservation of angular momentum, magnetic field lines are squeezed closer together, amplifying their strength. In some rare cases, this amplification is extreme. The newborn neutron star locks in a magnetic field so powerful that it never truly relaxes. What results is a magnetar. From the outside, a magnetar may appear unremarkable most of the time. It does not shine steadily like a star. It does not announce itself continuously. It drifts quietly, rotating, cooling, seemingly calm. But beneath that calm surface, enormous stress is accumulating. Magnetic fields are not static. They store energy. In a magnetar, the field threads through the star's crust and interior, exerting pressure on the rigid lattice of matter. Over time, this pressure builds. The crust resists, Much like a tectonic plate under strain, eventually resistance fails. When the crust of a magnetar cracks, the release of energy is sudden and immense. These events, known as magnetar flares, can outshine entire galaxies for brief moments. They release more energy in a fraction of a second than the sun emits in thousands of years, and yet even here, there is no explosion in the conventional sense. The star does not break apart, it does not disintegrate, it adjusts. The flare is the sound of tension releasing, not of structure failing. Afterward, the magnetar settles back into silence, its magnetic field slightly rearranged, its crust subtly reconfigured. The balance resumes. What makes magnetars particularly fascinating is how their magnetic fields interact with matter around them. At distances where a neutron star's gravity still dominates motion, a magnetar's field can dominate structure. It can polarize empty space, distort the paths of charged particles, and influence radiation itself. In extreme cases, the field is strong enough to affect the shape of electron orbitals in atoms. This is not metaphorical. The geometry of atomic structure can be altered by the presence of the field, even far from the star's surface. Physics here is not broken, it is strained. The equations still apply, but they operate in regimes we rarely encounter. Quantum electrodynamics predicts that at sufficiently high magnetic fields, empty space itself becomes nonlinear. Virtual particles flicker into brief existence, light can scatter from light. The vacuum behaves less like emptiness and more like a medium. Magnetars push us into these regimes naturally. They are laboratories for physics at its edge, places where theories are tested not by design, but by necessity. When a magnetar flares, it sends signals across the cosmos that carry information about magnetic reconnection, crustal strength, and the behavior of matter under conditions we cannot reproduce. And importantly, these signals are clean. They are not buried behind event horizons. They are not hidden from view. They arrive at our detectors as sharp, unmistakable bursts, brief messages from an object operating near the maximum allowed intensity of magnetism. There is also something deeply humbling about how rare magnetars are. Not every neutron star becomes one. Their formation requires a precise combination of mass, rotation, and magnetic inheritance. Too little, and the field remains ordinary. Too much, and collapse may continue toward a black hole. Once again, extremity appears not as excess but as balance. A magnetar exists because it sits within a narrow window where magnetic energy is allowed to dominate without destroying the star outright. The same gravity that holds the star together also contains the magnetic field, preventing it from tearing the structure apart entirely. This containment is not gentle. The crust of a magnetar is under constant stress. The interior may host magnetic configurations that twist and knot over time. Some models suggest that magnetars are born rapidly spinning, their rotation helping to amplify the magnetic field through dynamo processes early in their lives. As they age, they slow down, but the magnetic field remains, decaying only gradually. This decay releases energy continuously, heating the star's surface and making magnetars unusually bright in X-rays compared to other neutron stars of similar age. Brightness here does not mean warmth in the familiar sense. It means that magnetic energy is being converted into radiation, a slow leak of stored tension. Most of the time, this leak is quiet. Then, occasionally, it is not. The largest magnetar flares are among the most energetic events ever recorded in our galaxy. They can affect Earth's ionosphere from tens of thousands of light years away. Satellites have detected them as brief saturations, overwhelming instruments designed to measure distant cosmic explosions. And yet, these flares do not signal the death of the star. They are expressions of its continued existence. A magnetar does not explode because it is unstable. It flares because it is too stable to fail catastrophically. The energy must go somewhere, and it goes outward in flashes rather than inward in collapse. This distinction matters. It reinforces a theme that has been emerging throughout our journey. The most extreme objects are not those that break the rules. They are those that obey them under the most demanding conditions imaginable. Magnetars obey gravity. They obey quantum mechanics. They obey electromagnetism. They simply do so at levels that stretch our intuition until it almost fails. As you lie quietly now, your body is surrounded by magnetic fields, faint, harmless, unnoticed. Somewhere far away, a magnetar exists whose field could erase magnetic data, distort matter, and damage electronics from distances larger than planets. And yet, both are manifestations of the same force. This continuity is soothing. It means that extremity does not require a separate universe. It arises naturally when familiar laws are applied without compromise. Magnetars are not exotic exceptions. They are honest outcomes. They show us that magnetism, often treated as secondary to gravity in cosmic discussions, can become a primary actor under the right condition. They remind us that forces we take for granted can dominate entire worlds when given enough density, enough compression, and enough time. As we continue, magnetars prepare us for an important realization. If matter can remain stable under such intense gravity, if it can spin near light speed without tearing apart, if it can host magnetic fields that strain the vacuum itself, then we must reconsider what we mean by extreme, because the universe is not content with testing one limit at a time. It layers them. And in the next step of our journey, we will see what happens when density, rigidity, and gravity combine to produce a surface stronger than anything else we know, a surface that barely yields, even under the weight of stars. That is where we go next. Part 9. A surface. Harder than any known material. The crust of a neutron star is believed to be the strongest material in the universe, not because it is rigid, but because it is bound by gravity so intense that breaking it requires stellar-scale energy. Mountains on these stars are only centimeters tall, yet they store enormous strain, quietly waiting. When we think of strength, we usually think of resistance to bending or breaking, steel beams, diamond lattices, materials engineered to withstand pressure without yielding. But the strength of a neutron star's crust is something entirely different. It is not strong because it resists gravity. It is strong because gravity refuses to let it fail. On Earth, mountains rise kilometers high because the planet's gravity is relatively gentle. Rock can pile upon rock, supported by the rigidity of minerals and the slow flow of tectonics. But on a neutron star, gravity is so fierce that even the strongest imaginable material can barely lift itself at all. Any attempt to rise is punished immediately, crushed flat by the star's pull. And yet, the crust does rise, just barely. The mountains on a neutron star are not mountains as we would recognize them. They are tiny deformations in the crust, often no taller than a few centimeters. Some may reach a meter in extreme cases. But despite their modest height, these structures contain enormous amounts of energy. Because on a neutron star, even lifting matter by a few centimeters means fighting gravity with unimaginable force. This is why the crust is considered so strong, not because it is unbreakable in the human sense, but because it can sustain immense stress before yielding. Calculations suggest that neutron star crusts can support strains billions of times greater than any material we can test on Earth. The forces involved are so large that even the strongest terrestrial substances would behave like soft clay by comparison. The crust itself is only a thin shell, perhaps a kilometer thick, wrapped around a core of even stranger matter. Yet this thin shell carries the responsibility of maintaining the star's shape, anchoring its magnetic field, and responding to the relentless stresses imposed by rotation and gravity. To understand how such a crust forms, we must return to the moment of collapse. As a massive star implodes, its outer layers rebound and explode outward, but the core compresses inward, rapidly cooling and solidifying. Neutrons arrange themselves into dense configurations, and at the outermost layers, nuclei form a rigid lattice embedded in a sea of degenerate electrons. This lattice is not static. It is under constant strain. The star's rotation tries to distort it. The magnetic field threads through it, tugging and twisting. Gravity presses down from above, unyielding. Over time, stress accumulates. The crust bends slightly, storing energy like a compressed spring. But unlike a spring, the crust cannot release that energy gradually. There is no gentle flexing. There is only resistance, until there is failure. When the crust finally cracks, the release is sudden. These events are known as starquakes. They are the neutron star equivalent of earthquakes, but on an entirely different scale. When a starquake occurs, the crust rearranges itself abruptly, releasing stored energy into the star's magnetic field and surrounding space. The result can be a sudden change in the star's rotation, a burst of radiation, or a shift in its magnetic configuration. But once again, the star survives. The crust reforms. The balance returns. This cycle, stress, resistance, release, is another example of how extremity manifests not as destruction, but as endurance. The strength of the crust is also essential for another reason. Those tiny surface irregularities, those barely perceptible mountains, can make neutron stars visible in entirely new ways. As the star spins, any asymmetry in its mass distribution produces gravitational waves, ripples in space-time that propagate outward at the speed of light. These waves are incredibly weak by the time they reach us, but they carry pristine information about the star's internal structure. The height of a mountain measured in centimeters can determine whether a signal is detectable across thousands of light years. This sensitivity highlights how finely tuned these objects are. On Earth, centimeters are trivial. On a neutron star, they are cosmic signatures. The crust's strength also constrains how fast a neutron star can spin. If rotation becomes too rapid, stresses at the equator increase. The crust must hold together against centrifugal forces trying to pull it apart. That it can do so at hundreds of rotations per second speaks volumes about its resilience. But resilience does not mean permanence. Over very long timescales, neutron stars cool. Their interiors change subtly. Magnetic fields decay, rotation slows. As conditions evolve, the stresses within the crust shift. New cracks form, old ones heal. The star is never static, even though change happens slowly and quietly. This slow evolution is part of what makes neutron stars so fascinating. They are not frozen relics. They are dynamic systems operating on timescales far longer than human history. And through it all, the crust continues to do its quiet work, holding together matter at densities that should not exist, resisting forces that should tear it apart, and yielding only when the universe demands it. It is tempting to think of the crust as merely a surface feature, something secondary to the star's core. But in many ways, it is the interface between the star and the rest of the cosmos. It is where magnetic fields anchor, where radiation escapes, where changes in rotation are communicated outward. Without the crust, much of what makes neutron stars observable would vanish. There is also something deeply poetic in the idea that the strongest material in existence forms not through careful design, but through collapse, through matter stripped of its choices, forced into configurations dictated by necessity. The crust is strong because it had no alternative. As you lie quietly now, the ground beneath you feels solid because electromagnetic forces hold atoms apart. That solidity feels absolute. On a neutron star, solidity is redefined. It is not about atoms repelling one another. It is about gravity refusing to allow separation. This inversion challenges our intuition. Strength in this context is not independence. It is confinement. The crust does not hold together because it wants to. It holds together because it must. Gravity gives it no escape, and in that confinement, matter discovers how much strain it can endure. That discovery is not academic. It feeds directly into our understanding of fundamental physics. By studying starquakes, crust oscillations, and rotational glitches, sudden changes in spin, we gain insight into how matter behaves at densities far beyond nuclear matter. Each glitch is a message. Each quake is a data point. Each tiny mountain is a testament to endurance under impossible conditions. And importantly, none of this requires speculation about hidden interiors or unreachable singularities. The crust exists, it cracks, it radiates, it speaks. This is why neutron stars continue to challenge our assumptions about extremity. They show us that the most extreme states of matter are not abstract. They are tangible, measurable, and active. A surface only centimeters high can matter more than mountains thousands of meters tall. A crack invisible to the eye can release more energy than all human industry combined. Scale loses its meaning here. Only limits remain. As we move forward, this idea will become even more pronounced, because beneath the crust, matter enters states that defy simple description, and above it, time and space themselves begin to behave differently. But for now, let this settle. The strongest material in the universe is not forged in fire. It is not mined. It is not built. It is pressed into existence by gravity, held together by quantum law, and shaped by patience. And as quietly as it forms, it waits, bearing the weight of a star 1 centimeter at a time. Part 10. Pulsars and the precision of collapse. Some neutron stars emit beams of radiation so regular they rival atomic clocks. As they spin, these beams sweep across space like lighthouse signals. Each pulse marks a rotation, unchanged for millions of years. This precision is not engineered. It is the natural outcome of extreme gravity enforcing order on chaos. At first glance, pulsars seem almost intentional, as if they were designed to keep time. Their signals arrive with astonishing regularity. Some tick once every second, others pulse hundreds of times per second. A few are so stable that astronomers use them to test fundamental physics, detect gravitational waves, and even navigate spacecraft across the solar system. But pulsars are not machines. They are remnants. To understand how such precision emerges, we must return once more to collapse, not as destruction, but as refinement. When a massive star dies and leaves behind a neutron star, nearly everything that could vary is stripped away. Temperature becomes irrelevant. Chemical composition vanishes. The star's history is erased down to a few essential properties: mass, rotation, and magnetic field. What remains is simplicity enforced by gravity. A pulsar is a neutron star whose magnetic axis is misaligned with its rotation axis. This misalignment causes beams of radiation to stream outward from the magnetic poles. As the star spins, those beams sweep through space. When one crosses Earth, we detect a pulse. The lighthouse analogy is often used, but it understates the precision involved. A lighthouse beam may wobble slightly, distorted by wind or structure. A pulsar's beam does not. Its timing is governed by the inertia of a city-sized object containing more mass than the Sun, spinning freely in near-perfect vacuum. Once set, that motion barely changes. This stability arises from the neutron star's extreme compactness. Because the star is so small and massive, it has an enormous moment of inertia relative to its size. External influences, passing gas, radiation pressure, even nearby stars, have almost no effect on its rotation. There is simply too much mass packed into too little space to be disturbed easily. Rotation, once established, becomes destiny. This is why pulsars are so reliable. They are isolated, they are rigid, and they are governed by laws that allow almost no room for drift. A pulsar's spin may slow over millions of years as it radiates energy, but this slowdown is itself predictable. Each pulse arrives not randomly, but according to equations that can be written and tested. There is something deeply comforting about this. In a universe filled with turbulence, collisions, explosions, chaos, pulsars offer steadiness. They are cosmic metronomes ticking away long after the violence that created them has faded. This steadiness also reveals something important about collapse. Collapse is often imagined as disorder increasing, structure breaking down. But in the case of neutron stars, collapse does the opposite. It removes degrees of freedom. It simplifies. It leaves behind an object whose behavior is easier to predict than the star that came before it. The massive glowing star was complex. Fusion zones shifted. Convection cells churned. Magnetic fields tangled and reformed. The pulsar is simpler. Its internal motions are constrained. Its structure is rigid. Its rotation is clean. Collapse here is not entropy increasing. It is entropy being compressed. That compression produces precision. Pulsars also remind us that extreme gravity does more than bend space. It disciplines matter. It enforces alignment. It dampens irregularities. Anything that does not conform is stripped away during formation. Only the most stable configurations survive. This is why pulsars can maintain timing accuracy better than many human-made clocks. Atomic clocks rely on carefully controlled laboratory conditions. Pulsars rely on gravity, inertia, and vacuum. They do not drift because there is almost nothing that can make them drift. Some pulsars are so reliable that deviations in their timing can signal events occurring light years away. Slight changes in pulse arrival times can reveal the presence of orbiting companions, passing gravitational waves, or subtle shifts in space-time itself. In this way, pulsars become instruments, not built by intention, but by inevitability. Their existence also highlights an important truth about extreme objects. Extremity does not mean unpredictability. In many cases, it means the opposite. When systems are pushed to their limits, unnecessary complexity falls away, leaving behind behavior that is almost austere in its regularity. There is also something profound about the scale of this precision. Each pulse you detect from a distant pulsar began as a rotation of a star that collapsed millions or billions of years ago. That rotation has continued uninterrupted through epochs of galactic change, through the formation and destruction of countless other stars, through the slow drift of continents on Earth. The pulse does not care. It arrives when it must. As you rest now, breathing slowly, imagine a pulse traveling through space. It passes between stars, through clouds of gas, across empty regions where nothing changes for eons. It arrives at a detector on Earth at the exact moment predicted, not because anything guided it, but because nothing interfered. That is the quiet power of isolation and inertia. Pulsars also show us how collapse can amplify small imperfections into defining features. The slight misalignment between magnetic and rotational axes, perhaps insignificant in the parent star, becomes everything in the remnant. Without that misalignment, the pulsar would be silent. With it, the star announces its existence across the galaxy. Extremity, again, reveals what matters. Even the smallest asymmetry can become meaningful when everything else has been stripped away. There are different kinds of pulsars, each reflecting a different path through collapse and evolution. Some are young, spinning rapidly, losing energy quickly. Others are ancient, spun up again through interactions with companion stars, rotating hundreds of times per second with astonishing stability. These recycled pulsars are among the most precise clocks known. Their long histories have smoothed out irregularities, their crusts have adjusted, their magnetic fields have settled into configurations that change only slowly. They are old, quiet, and exact. This longevity adds another layer of calm to their story. Pulsars are not brief phenomena. They are not flashes. They are enduring signals that persist across cosmic time. In their steadiness, they offer a sense of continuity that is rare in astrophysics. Violence creates them. Calm defines them. This duality runs through everything we have explored so far. Massive stars live turbulent lives, yet their remnants are often serene. Gravity destroys, yet also organizes. Quantum rules resist collapse, yet allow precision. Nothing here is contradictory. It is all consequence. Pulsars also remind us that measurement itself depends on stability. We can detect gravitational waves, test relativity, and map the galaxy using pulsars because they are dependable. In a sense, the universe has provided its own reference points, scattered across space, ticking quietly. We did not ask for them. They arrived anyway. As we move forward, this idea of precision will remain important, because the more extreme an object becomes, the fewer ways it can behave. Choices narrow, paths converge, behavior simplifies. This is why neutron stars, despite their exotic nature, are often easier to model than ordinary stars. Their complexity has been burned away by collapse, leaving behind clarity. And pulsars are the clearest expression of that clarity. They tell us that collapse is not always an end, that extremity can produce order, that precision can emerge from catastrophe. Each pulse is a reminder. The universe does not rush. It does not improvise. It follows its rules to their logical conclusions. And sometimes those conclusions tick, steadily, quietly, across the dark. Part 11. The boundary. Before a black hole. There is a threshold where neutron stars can no longer resist gravity. Beyond a certain mass, collapse becomes unavoidable. But just before that boundary lies the most extreme stable state matter can reach. This edge, between existence and disappearance, is where the universe seems to pause, deciding whether something may remain or vanish forever. To understand this boundary, it helps to imagine gravity as a question that grows louder with mass. For small objects, the question is quiet, easily answered by the rigidity of matter and the spacing between atoms. For stars, the question grows more demanding, answered by nuclear fire and outward pressure. For neutron stars, the question becomes relentless, pressing inward with a force so intense that only the deepest rules of physics can respond. And yet, for a time, those rules answer back. A neutron star exists because gravity has been pushed almost to its limit, but not quite. Quantum mechanics and nuclear forces still have something to say. They hold the line, allowing matter to remain visible, measurable, and structured, though only barely. But there is a line. This line is not drawn in space, it is drawn in mass. If a neutron star grows too heavy, perhaps by pulling matter from a nearby companion star, or by merging with another neutron star, the delicate balance that sustains it begins to unravel. The pressure holding neutrons apart increases, but gravity increases faster. The rules that once resisted collapse begin to lose their leverage. Physicists call this limit the maximum neutron star mass. It is not a single precise number, but a range shaped by the unknown details of matter at extreme density. Observations suggest it lies somewhere around 2 to 3 times the mass of the Sun. That may not sound like much, but here, a fraction of a solar mass makes all the difference between endurance and disappearance. As a neutron star approaches this threshold, something remarkable happens. The object does not become unstable in a dramatic way. There is no warning flare, no sudden shudder. From the outside, it may look much like any other neutron star, spinning, radiating, pulsing with quiet regularity. Internally, however, the margin for balance is shrinking. Every additional particle adds weight, without adding new ways to resist. Neutron degeneracy pressure cannot grow indefinitely. The strong nuclear force can only do so much. There comes a point where the inward pull of gravity cannot be countered by any known mechanism. At that point, collapse resumes. What makes this boundary so extraordinary is how abrupt the transition is. Below the limit, matter remains. Above it, matter disappears behind an event horizon. There is no gradual fade from neutron star to black hole. One moment, the object has a surface, a crust, a measurable radius. The next, it does not. This sharpness gives the boundary a philosophical weight that few other phenomena possess. It is a genuine edge, not of space, but of possibility. On one side, the universe allows matter to exist in its most compressed, strained, and disciplined form. On the other, it does not. The difference between the two may be as little as the mass of a mountain added to an object already heavier than a star. This is not metaphor. It is measured. There is something deeply humbling about how narrow this window is. It suggests that the universe tolerates complexity only up to a point. Beyond that, it simplifies radically. It does not negotiate endlessly. It decides, and yet that decision is not arbitrary. The boundary exists because the laws of physics are consistent. They do not bend further to accommodate heavier neutron stars. They do not invent new pressures at the last moment. When resistance fails, collapse follows. This consistency is what allows us to speak meaningfully about extremity. The most extreme stable object is not defined by our imagination, but by the rules themselves. It is defined by what physics permits, not by what feels dramatic. In this sense, neutron stars at the upper mass limit are among the most profound objects in existence. They embody the final compromise between gravity and matter. They are not endpoints, they are thresholds. Standing at this boundary, matter has exhausted every known way to remain itself. This is why the question of the neutron star maximum mass is so important to science. It tells us not just about stars, but about the nature of matter under ultimate compression. Different theories predict different limits. Some allow heavier neutron stars by invoking stiffer equations of state. Others predict lower limits, suggesting that black holes form more readily. Each new observation, a neutron star measured slightly heavier than expected, pushes this boundary outward, refining our understanding of what matter can endure. And still, the boundary remains. There's also something quietly poetic about where this boundary sits. It is not at the largest scales. It is not at the smallest. It exists in a middle ground, where quantum mechanics, nuclear physics, and general relativity all matter equally. Few places in the universe demand that all three be obeyed simultaneously. At this edge, time itself begins to behave differently. As gravity intensifies, time slows relative to distant observers. Signals leaving the star are increasingly redshifted. The star's surface appears more and more reluctant to let anything escape. From the outside, the difference between a neutron star at the limit and a black hole forming may be subtle, until it is not. Then, suddenly, the surface is gone. This disappearance is not violent in the way explosions are violent. It is quiet, sudden, final. The star does not explode into nothingness. It collapses inward, crossing a boundary beyond which the universe no longer returns information. What was once the most extreme stable object becomes something else entirely. This sharp transition reinforces an important idea. Extremity is not about infinity. It is about limits. The universe does not like infinities. When equations predict them, something changes. A new description becomes necessary. Neutron stars exist precisely because they avoid infinity. They stop just short of it. This makes them feel almost intentional, though they are not. They are what happens when physics is pushed as far as it can go without breaking its own rules. As you rest now, there is a sense in which you are always near boundaries too. The boundary between sleep and wakefulness, between thought and silence, between effort and rest. These boundaries feel gentle, but they are real. The universe has its own boundaries, far less gentle, yet governed by the same quiet inevitability. The boundary before a black hole is one of the most profound of these. It is where the universe decides whether complexity may continue to exist openly or whether it must be hidden forever. And that decision is made not with noise, but with mass. There is no appeal process, no adjustment period. Once the limit is crossed, the outcome is fixed. But until that moment, until the final gram is added, the neutron star remains, holding itself together, spinning, pulsing, bearing gravity's question and answering it with everything it has. That answer is temporary, but it is real. And in that temporary resistance lies something extraordinary, a demonstration that matter, governed by quantum law, can oppose gravity almost to the end. That existence itself is allowed, but only within precise bounds. As we continue, this realization will sharpen, because once we understand this boundary, we can begin to see why neutron stars, not black holes, may truly deserve the title of the most extreme objects the universe allows us to observe. Not because they win forever, but because they hold on until the very last possible moment. Part 12. Why density isn't the whole story. Black holes are denser, yes, but density alone does not define extremity. Inside a black hole, matter disappears from the observable universe. In neutron stars, matter remains exposed, compressed, spinning, glowing, resisting collapse. Extremity, in this sense, is not about disappearance, but endurance. It is tempting to rank the universe by simple numbers: bigger, heavier, denser, faster. By that logic, black holes seem to win every comparison. Their densities rise beyond comprehension. Their gravity dominates everything nearby. Their interiors vanish behind horizons we cannot cross. But physics is rarely impressed by single numbers in isolation. What matters is not just how extreme a quantity becomes, but what that extremity demands in return. Density tells us how much mass is packed into a given volume. It is an important measure, but it does not tell us how matter behaves under that compression. It does not tell us whether structure survives, whether forces still balance, or whether the laws of physics are still actively at work in a visible way. In black holes, density leads to concealment. Matter is no longer available to observation. Whatever complexity exists inside is hidden permanently from the outside universe. From our perspective, the story ends at the horizon. In neutron stars, the story continues. Matter remains present, measurable, and active. It rotates, it vibrates, it cracks, it emits radiation, it responds to forces and broadcasts its state across space. Density here is not an endpoint. It is a condition under which endurance is tested continuously. This difference is subtle but profound. A black hole answers gravity by surrendering completely. A neutron star answers gravity by negotiating, again and again, moment by moment, under conditions that allow no margin for error. That negotiation is what makes neutron stars so revealing. To see why density alone is insufficient, consider a thought experiment. Imagine compressing matter more and more. At first, atoms resist through electromagnetic forces. Then, electrons resist through degeneracy pressure. Then, neutrons resist through their own exclusion rules and nuclear interactions. At each stage, new physics emerges to oppose collapse. Each stage is extreme in its own way. But when collapse continues into a black hole, resistance ends. The physics that once balanced forces is no longer accessible to us. The universe does not show us how matter behaves there. It hides the answer. That hiding is not extremity of behavior, it is extremity of consequence. Neutron stars, by contrast, sit at the point where behavior is most demanding and most visible. Matter must obey quantum mechanics, nuclear physics, and relativity simultaneously, and it must do so without disappearing. Every property of the star reflects this effort. Its mass tells us how stiff matter is. Its radius tells us how compressible matter can be. Its spin tells us how rigidity survives rotation. Its magnetic field tells us how charged particles behave under extreme confinement. None of this information is available from inside a black hole. So while black holes may be denser, they are simpler from the outside. They are described by only a handful of parameters. Neutron stars, though slightly less dense, are far richer in physical expression. Extremity, then, is not about how far you go. It is about how much you must manage when you get there. There is also a deeper philosophical reason density alone falls short. Density is a scalar quantity. It has magnitude but no direction. It tells us nothing about internal structure, motion, or balance. Extremity in physics is often about competing tendencies, not just large values. Neutron stars are extreme because they hold contradictory demands in equilibrium. Gravity demands collapse. Quantum mechanics demands spacing. Nuclear forces demand cohesion at short range. Rotation demands outward motion. Magnetism demands structure and alignment. All of these demands coexist in a neutron star. None is allowed to dominate completely. The result is not simplicity, but tension held in place. That tension is what we observe. In a black hole, many of these demands still exist, but we cannot see how they resolve. The universe closes the curtain. Density becomes infinite in theory, but descriptive power becomes finite. This is why endurance matters. Endurance means remaining within the universe of observation. It means continuing to answer questions rather than ending them. Neutron stars endure not because conditions are mild, but because conditions are harsh and precisely balanced. Even their failures are informative. When a neutron star collapses into a black hole, the event marks the exact point where endurance was no longer possible. That boundary teaches us more than the black hole itself ever could. This idea reshapes how we think about extremes. The most extreme state is not necessarily the one that goes furthest, but the one that remains coherent under the greatest strain. Think of a bridge again. The bridge that collapses under weight tells you something, but the bridge that holds just before collapse tells you everything about materials, design, forces, and limits. Neutron stars are bridges under cosmic load, and they are still standing. There's also something quietly comforting about this perspective. It suggests that the universe values balance over absolutes, that it allows matter to explore the edge of possibility without immediately erasing it, that the most demanding environments are not hidden from view, but placed on display. As you lie quietly now, your own body is an exercise in endurance at a vastly smaller scale. Cells maintain structure against thermal motion. Proteins fold correctly despite constant agitation. Balance is maintained not by force alone, but by rules and constraints. The same is true of neutron stars, just magnified beyond imagination. Density is part of their story, but it is not the climax. The climax is the ongoing act of holding together, of continuing to exist under conditions that would destroy anything less constrained. This is why neutron stars feel more extreme the longer we study them. Each new observation adds detail, not mystery. Each new measurement tightens constraints, revealing just how narrow the allowed window really is. Black holes feel extreme because they are unknowable. Neutron stars are extreme because they are knowable under impossible conditions. That difference matters. It tells us where physics is most alive, where laws are most actively engaged, where the universe is not silent, but speaking in precise, measurable ways. And it leads us naturally to the final question. If extremity is not about disappearance, if it is not about infinity, if it is not about density alone, then what is the most extreme thing the universe allows us to witness? The answer has been forming quietly across every part of this journey, and in the next step, we will gather those threads together to see why endurance itself may be the true measure of extremity, and why neutron stars, in their stubborn refusal to vanish, may stand unmatched, not because they are the densest, but because they remain. Part 13. The sound of a star breaking. When neutron stars collide, they send ripples through space-time itself. Gravitational waves carry the signature of matter under ultimate stress. These waves are not violent noises, but faint echoes, recordings of reality reaching its limits and briefly exceeding them. For most of cosmic history, these sounds passed unnoticed. Space stretched and compressed in silence, carrying information no ear could hear and no instrument could record. Collisions happened far away, in distant galaxies, their consequences written into the fabric of space-time itself, then fading as they traveled outward at the speed of light. Only recently have we learned how to listen. Gravitational waves are not vibrations of air or bursts of sound in the familiar sense. They are distortions, gentle lengthenings and shortenings of space itself. When massive objects accelerate, especially when they orbit or collide, they create these ripples. Most sources are too weak to matter, but neutron stars, dense and fast-moving, can shake space-time in measurable ways. A neutron star collision is not sudden. Long before the final impact, two stars begin a slow, inevitable dance. They orbit each other, losing energy through the emission of gravitational waves. With each orbit, they spiral closer. The frequency of the waves increases, the rhythm quickens. This gradual rise, the chirp as physicists call it, is the universe counting down. As the stars draw nearer, tidal forces grow enormous. Each star begins to stretch the other, pulling at its surface, distorting its shape. Matter that has resisted gravity for millions of years is now being asked to endure something new, the pull of an equal partner. The crusts strain, internal structures deform. Quantum-supported matter is tested not just by gravity, but by violent curvature of space-time. This is the sound of a star breaking, not in explosion, but in negotiation, failing. At the moment of collision, the stresses exceed anything a neutron star can withstand. The stars crash together at a significant fraction of the speed of light. Their structures collapse inward and outward simultaneously. For a brief instant, matter exists in states that challenge even our best theories. Then, depending on the combined mass, one of two things happens. Either a more massive neutron star forms, temporarily held together by rapid rotation and intense pressure, or collapse continues, and a black hole is born. In both cases, gravitational waves carry away the details. What makes these waves so extraordinary is not just their origin, but what they encode. Unlike light, which interacts with matter and can be scattered or absorbed, gravitational waves pass through almost everything unchanged. They arrive at Earth as clean records of the event that created them. They tell us how massive the stars were, how fast they were spinning, how stiff their matter must have been, how close they came to the ultimate limit before breaking. This is why neutron star mergers are among the most valuable events in modern astrophysics. They allow us to probe matter under conditions that cannot be sustained anywhere else. For a fraction of a second, densities exceed those inside stable neutron stars. Pressures rise. Forces compete at levels that may briefly exceed the usual boundaries. Reality, for a moment, goes further than it is normally allowed. And then it retreats. The waves that carry this story outward are astonishingly gentle by the time they reach us. When detectors on Earth register a neutron star merger, the distortion they measure is smaller than the width of a proton over kilometers of distance. And yet, from that faint signal, we can reconstruct events that involved objects heavier than stars colliding across millions of light years. There is something deeply moving about this contrast. The most extreme violence in the cosmos announces itself as the softest whisper imaginable. This softness fits perfectly with the theme we have been following. Extremity does not shout. It reveals itself through precision, through subtlety, through patterns that must be measured carefully, patiently, respectfully. When the first neutron star merger was detected through gravitational waves, it confirmed decades of theory. But it also offered something more, a direct glimpse into the moment when endurance ends. Up until that final instant, each neutron star had held itself together. It had balanced gravity with quantum law. It had survived rotation, magnetism, and time. In the merger, that balance is overwhelmed, not gradually, but decisively. This is the edge we have been circling. The sound of a star breaking is the sound of resistance giving way. But even here, there is order. The waves follow equations. Their frequencies and amplitudes evolve predictably. There is no randomness in how space-time responds. Even at its limits, the universe remains lawful. This lawfulness allows us to ask questions we could never ask before. How stiff is neutron star matter? How quickly does collapse occur? Does exotic matter appear briefly before disappearance? How much mass can be supported even for a moment? Each merger answers some of these questions and raises others. Each detection refines our understanding of where the true boundary lies. There is also a quiet continuity in how these events connect to everything else we have discussed. The crusts that once cracked in starquakes now shatter completely. The rotation that once stabilized the star now accelerates collapse. The density that once defined endurance now defines failure. Nothing changes suddenly. Everything flows from what came before. Even the aftermath is telling. The merger does not simply erase the stars, it enriches the cosmos. Heavy elements, gold, platinum, and others, are forged in the chaos and scattered into space. The most demanding environments give rise to the materials that will one day form planets and perhaps life. Extremity feeds creation. As you rest now, the idea that the gold in your world may have been born in the sound of a star breaking carries a quiet weight. It connects the most delicate things to the most extreme events. It reminds us that boundaries are not just endings, they are transitions. The gravitational waves themselves continue outward long after the stars are gone. They pass through galaxies, through clusters, through empty space. They cross the universe carrying their message unchanged. They say, "This happened. This much mass, this much strain, this was the limit." And then they fade. There is something deeply calming in knowing that even the universe's most intense moments resolve into gentle echoes, that nothing lingers in chaos, that after every collision, space-time smooths itself again. The sound of a star breaking is not a scream, it is a sigh, a final release of tension stored over millions of years, carried away so softly that only the most sensitive instruments can hear it. And in that sound, we hear confirmation of everything we have been exploring, that neutron stars truly do live at the edge, that they endure until endurance is no longer possible, that when they fail cleanly, leaving behind not confusion, but information. As we approach the final parts of this journey, these echoes will stay with us, because they show us that the most extreme objects are not defined only by how they live, but by how they end, quietly, precisely, and in a way that teaches us more about reality than any spectacle ever could. The universe does not announce its limits with noise. It lets them be heard only by those who are listening. Part 14. What these objects teach us about reality. Neutron stars are laboratories we did not build. They test theories we cannot recreate on Earth. Every observation refines our understanding of matter, space, and time. They remind us that nature does not need extremes often, but when it creates them, it does so with extraordinary elegance. There is something humbling about learning from objects we cannot touch, cannot approach, and cannot reproduce. Neutron stars exist far beyond our reach, yet they shape our understanding of reality more deeply than many experiments conducted on Earth. They do not answer our questions directly. They respond to them through behavior, through mass and motion, through light and silence, through endurance, under conditions that strain our best ideas. In this way, neutron stars are not just objects of study, they are conversations. Each one speaks in a language made of gravity and time. Each one answers questions we did not know how to ask until we learned how to listen. One of the most profound lessons neutron stars teach us is that the laws of physics are universal. The same quantum rules that govern electrons in a laboratory govern neutrons inside a star heavier than the sun. The same equations that describe gravity near Earth describe gravity strong enough to bend space-time into tight curves. There is no separate set of rules for the extreme. There is only one set, applied without mercy. This consistency is not dramatic, but it is deeply reassuring. It tells us that reality does not fracture under pressure. It does not invent exceptions when things become difficult. Instead, it becomes more exacting, more constrained, more precise. Extremes do not break the laws of physics, they reveal them. Neutron stars also teach us that simplicity can emerge from complexity. A massive star is turbulent, layered, dynamic. Its interior churns with fusion and flow. Its surface seethes with motion. But when that star collapses, most of that complexity is erased. What remains is an object defined by just a few parameters, yet capable of astonishingly rich behavior. This is a recurring theme in nature. Complexity gives way to clarity at the edges. In neutron stars, collapse removes degrees of freedom. Chemistry vanishes. Thermal processes fade. What remains is matter governed almost entirely by fundamental forces and quantum rules. The result is not chaos but order, rigid, disciplined, and persistent. This teaches us something important about understanding reality itself. We often assume that complexity is a sign of depth, that the more intricate a system becomes, the more fundamental it must be. Neutron stars suggest the opposite. At the deepest levels, behavior simplifies. Laws become clearer. Variables disappear. Reality at its core may be simpler than we expect. Neutron stars also challenge our intuitions about scale. They show us that size and importance are not linked. These stars are tiny by cosmic standards, smaller than many cities, and yet they influence entire fields of science. Their gravitational waves reshape astrophysics. Their magnetic fields test quantum electrodynamics. Their rotation informs timekeeping and navigation. This inversion of scale is quietly profound. It reminds us that meaning in the universe does not come from largeness alone. It comes from constraint, from balance, from operating near limits. Another lesson neutron stars teach us is that matter is far more adaptable than we imagine. At everyday conditions, matter feels solid and familiar. At stellar conditions, it becomes plasma and fusion fuel. At neutron star conditions, it becomes something else entirely. Matter reorganized at a level where atomic identity no longer applies. And yet, even then, matter remains matter. It does not dissolve into abstraction. It continues to obey rules. It continues to resist compression. It continues to exist in definable states. This resilience suggests that the universe is built with layers of defense against collapse. That annihilation is not the default outcome, even under extreme stress. In this way, neutron stars teach us patience. Collapse is not immediate. Endurance is always attempted first. They also teach us that time is not absolute. Near neutron stars, time slows measurably. Clocks tick differently depending on where they are placed. This is not theory. It is observation. Signals from neutron stars carry the imprint of time dilation, confirming predictions made decades before we could test them. Time, like matter, responds to gravity. This realization reshapes how we think about experience itself. It tells us that time is not a backdrop against which events unfold. It is part of the fabric that responds to mass and motion. Neutron stars do not just exist in time, they sculpt it. Perhaps most importantly, neutron stars teach us humility. They remind us that our understanding is provisional, that even our most successful theories, quantum mechanics, relativity, are incomplete when pushed to their limits. The interiors of neutron stars remain partially mysterious. Their equations of state are not fully known. Their deepest layers may hold surprises we have not yet imagined. And yet, this mystery is not discouraging. It is inviting. It tells us that reality still has things to teach us, and that the most extreme environments are not closed books. They are chapters written in a language we are still learning to read. There is also a quiet ethical lesson here, though physics rarely frames it that way. Neutron stars show us that restraint is powerful, that holding together under pressure is itself a form of strength, that disappearance is not the only outcome when forces grow overwhelming. In a universe that often feels defined by destruction, neutron stars offer a counterexample. They show us endurance without sentiment, resistance without struggle, balance achieved not through will but through law. As you lie quietly now, there is something comforting in knowing that the universe does not rush to extremes, that it creates them sparingly, that when it does so with care, with precision, with elegance. Neutron stars are not accidents, they are not failures, they are achievements of natural law, objects that exist because the universe allows them to, and no longer. They sit exactly where they must. This exactness is perhaps their greatest lesson. That reality is not arbitrary. That even at its edges, it remains structured. That limits exist not to frustrate us, but to define what is possible. And in defining what is possible, neutron stars help us understand ourselves. They remind us that we too exist within limits, that stability matters, that endurance is meaningful, that balance, once achieved, can persist far longer than turmoil. As we approach the end of this journey, these lessons begin to settle into a single quiet insight. The most extreme objects are not the ones that vanish into darkness. They are the ones that remain visible at the brink. They are the ones that allow us to learn. Neutron stars do not shout their importance. They simply exist, dense, silent, precise, teaching us patiently what reality looks like when nothing is left to spare. Part 15. The universe's most patient resistance. The most extreme object in the universe is not defined by destruction, but by restraint, by matter pushed to the brink that still holds together. Neutron stars exist not because gravity is weak, but because the universe allows just enough resistance for something to remain. Throughout this quiet journey, we have followed gravity as it presses inward, asking the same question again and again. How much can you bear? At every stage, matter answers, sometimes gently, sometimes reluctantly, but always according to the same rules. Neutron stars are the final place where that answer is still spoken aloud. They are not the strongest because they dominate their surroundings. They are not the most extreme because they erase complexity. They are extreme because they endure. Endurance, in physics, is not romantic, it is not heroic, it is mathematical. It is what happens when competing laws cancel one another with extraordinary precision. Gravity pulls inward with relentless force. Quantum mechanics forbids certain arrangements. Nuclear forces bind at short distances and repel at others. Rotation adds tension, magnetism adds stress, and somehow, none of these is allowed to win completely. What remains is balance, narrow, exact, and astonishingly stable. This balance is patient. Neutron stars do not rage against gravity. They do not push back dynamically. They simply exist in a configuration where pushing further becomes impossible without changing the nature of reality itself. Gravity presses, but it cannot compress without paying an energetic cost that grows too steep. The universe does not forbid collapse outright, it simply makes it expensive. So gravity waits, and in that waiting, the neutron star remains. There is something deeply calming about this image, an object born from one of the most violent processes we know, a supernova, settling into a long, quiet existence defined not by turmoil, but by constraint. Millions of years pass, sometimes billions. The star spins, it cools, it pulses, it cracks occasionally, then heals. But it does not fall apart. This patience is not accidental. It is built into the laws themselves. Physics does not seek extremes for their own sake. It does not chase infinity. It allows matter to explore the edges of possibility carefully, step by step, stopping precisely where it must. Neutron stars are the clearest expression of this philosophy. They show us that the universe prefers continuity over collapse. That disappearance is a last resort, not a default. That matter is given every opportunity to remain visible, measurable, and structured before it is hidden away. In this sense, black holes are not the climax of gravity's story. They are the coda. The silence after resistance has ended. Neutron stars are the crescendo, the moment where all forces speak at once, none overpowering the others. This reframes how we think about extremity itself. Extreme does not mean unstable. Extreme does not mean chaotic. Extreme means exact. It means operating with no margin for error, with no excess capacity, with no slack in the system. Neutron stars are not forgiving objects. Add too much mass and they fail. Remove too much and they never form. They exist only within a narrow window that the universe maintains with unwavering consistency. That narrowness is the point. It tells us that reality is finely tuned not in the sense of intention, but in the sense of constraint. The laws of physics do not allow everything. They allow very little. And within that allowance, neutron stars occupy one of the most demanding positions possible. They are not merely dense, they are not merely fast, they are not merely magnetic. They are all of these at once, held together by refusal rather than force. As you lie quietly now, there's a gentle parallel to be drawn. Your body, too, is held together by balance. Cells resist collapse, structures endure tension, systems remain stable, not because forces are absent, but because they are balanced. Life itself is a form of patient resistance to entropy. Neutron stars are that idea, written in gravity and time. They remind us that strength does not always announce itself, that the most impressive achievements of nature are often silent, that the universe does not rush to extremes, but approaches them carefully, allowing matter to hold on as long as it possibly can. This patience is written into every neutron star we observe, into their precise spins, into their rigid crusts, into their predictable pulses, into the faint gravitational waves they emit when they finally meet their limits. Even when they fail, they do so cleanly. There is no chaos in the transition from neutron star to black hole. There is no struggle. There is simply a boundary crossed and a new description required. Until that moment, endurance is honored. This tells us something profound about reality. The universe does not value destruction. It values consistency. It values balance. Neutron stars are not mistakes. They are not leftovers. They are what happens when the universe applies its rules as far as they can go without contradiction. And because they exist at that edge, they teach us more than any other object we know. They teach us how matter behaves when nothing is left to spare. They teach us how time bends under weight. They teach us how quantum rules scale up to hold back stars. They teach us where limits truly lie. In this light, calling neutron stars the most extreme objects feels almost insufficient. They are not extreme in the way storms are extreme, or explosions are extreme. They are extreme in the way stillness can be extreme, in the way silence can be full, in the way patience can outweigh force. They are monuments to restraint, and perhaps that is why they feel so compelling to contemplate before sleep. They offer a vision of the universe that is not frantic, not violent, but deliberate. a universe that allows even its most intense forces to be balanced, if only for a time. As this journey draws toward its close, let that image linger. A star's core, crushed nearly beyond recognition, gravity pressing with all it has, quantum laws standing firm, matter holding together, not forever, but long enough. Long enough to be seen, long enough to be measured, long enough to teach us something true. The most extreme object in the universe is not the one that disappears. It is the one that stays, right up to the very last possible moment. And in that staying, in that quiet, patient resistance, the universe shows us not just its power, but its restraint. And that perhaps is the most extraordinary thing of all. As this quiet journey comes to rest, it's worth lingering for a moment on what we've gently uncovered. Not explosions or collapse, not disappearance or darkness, but balance. Matter holding together under the greatest pressure the universe allows. Forces meeting one another with perfect restraint. Endurance written into the fabric of reality. Neutron stars remind us that the cosmos is not defined solely by its most dramatic endings, but by its patience. By how long something can remain, even when everything is asking it to give way. They show us that the universe does not rush toward silence. It allows complexity to persist. It allows resistance. It allows time. As you breathe now, slow and steady, there is a quiet symmetry in knowing that the same laws holding your body together are the ones holding up stars crushed nearly beyond comprehension. The scale is different. The pressure is unimaginable. But the rules are the same, and they are consistent, calm, and precise. If this story has brought you a sense of stillness, of perspective, or of gentle awe, I'm deeply grateful you were here for it. Thank you for sharing this quiet space and for letting curiosity soften into rest. There is nothing more you need to hold on to tonight. The universe is doing what it has always done, balancing, enduring, moving forward with patience. You can let go now. The stars are still there, and so is the calm. Rest well.